Okay, good morning, everyone. We've been talking about fiber alignment and fiber dispersion, and we've been talking about properties of rheological properties of the mixture, and I think it's all related to fluid mechanics. So what I'm going to be talking about, it's all about fluid mechanics today. So I'm going to be the presentation is about CFD-DEM approach to model the behavior of fibers in fresh concrete. This is the first simulation, is our first draft. There's a lot of improvement to do, but we're probably going to be good at the end of this year. So as everybody has said before, UHPC is exceptional in strength and durability. It extends the lifespan of infrastructure, reduces maintenance needs, and increases structural resilience, mostly because of fiber cracking bridging. So post-cracking behavior is very good. It's a nice characteristic of UHPC. Cracking bridging, it happens due to the existence of fibers. So because of this, we want fibers to be well distributed in the directions that we need to have that bridging. So what we can do, this orientation might be affected by the rheology of the UHPC mixture, the casting method, the casting device, the formwork geometry, the structural element, the fiber aspect ratio, the fiber concentration, and the rebar arrangement. All together, not one by one. So we think we need tools to predict fiber orientation and dispersion. That's what we desire, to understand how does this work and how does UHPC behavior can be improved. We need to know what's going on at the micro scale or at the fiber scale. So what we propose, this is not new, is to construct a CFD-DEM model. So CFD is computational fluid dynamics, and you can use it to model the movement of the fluid, in this case a non-Newtonian fluid, which is the fresh concrete. And the DEM, which is discrete element method, would be a method to follow each fiber Lagrangianly. So we can't, with the CFD-DEM model, we should be able to predict the fiber orientation and dispersion in the UHPC, simulate fresh concrete as it flows and as it interacts with fibers, and also with the DEM, see how fibers interact to each other as we increase the concentration. So that will enable us to study all these different factors that affect the fiber orientation. But how does it work? So CFD uses the Navier-Stokes equation, 3 momentum equations, and a mass balance equation that couple together to follow the flow. Then the DEM, we need angular momentum and linear momentum equations based on the second Newton's law, where we have forces, hydrodynamic forces, and weight, and torque. And with that, if we couple them together with the final force there in the momentum equation for the fluid, we can have two-way coupling, which means the flow will move the fibers, but as we increase the fibers will hit back the flow and change its behavior. So if we're able to compute all this information, we'll be able to know the location of each fiber at each time step. We'll be able to predict the dispersion, the orientation, and maybe work out how can we improve the orientation and the dispersion of the fiber for each application. So the CFD, in our case, the first simulation we did, this is the experimental setup. We use a beam, small beam of 300 millimeters in length, 75 millimeter in section, transversal section. We use an L-shape casting device that holds 1.75 liters of mixture. We had to do the mixture because we needed the rheology in order to input it into the CFD program. So, and we tried to apply this setup. So we have an L shape that is put vertically and the flow is coming from one end. Of course, we took this final beam into a CT to understand the fiber orientation and dispersion. at the end of the test. We took a sample of that mixture and we put it into a rheometer. We got the Hershey-Berkeley equation to fit the experimental points, and we got a yield stress of 23.62, a consistency index of 36.16, and a flow index of 0.85. So we inputted that into our CFD model to model the behavior of the mixture. And now we have to take care of the discrete element method simulation. So what we do is we do have fibers of around 20 millimeters in length, 0.38 millimeters in diameter, an aspect ratio of about 55. We replace this fiber with several spheres of 0.38 millimeters, and which makes 55 spheres to mimic the behavior of the actual fiber. So we use fibers, they're glued together, so there are many equations here on how to connect the fibers, how do they tort, how do they flex. There's no flexibility in this case, but we might be able to do flexibility if we want to, if we have mixtures. We have steel fibers and plastic fibers, for example. We use random collocation at the L-shaped casting device with 45 degrees minus and plus 45 degrees from the vertical. We use 1,300 fibers, applying hydrodynamic forces of drag, lift, virtual mass, buoyancy, which is basically submerged weight, and we apply collisions with the fibers to the wall and between fibers. Since we have a very sophisticated collision algorithm, we can have many fibers colliding to themselves at the same time. This is the computational domain. So we have the L-shaped device. We have the beam right here. We have air. So we have three phases. We have air. We have solids, which are the fibers that we're following. And we have the mixture, which is our non-Newtonian liquid. This is the fixed mesh that we're using. We're around 31,000 cells. This is our first experiment. We should increase the amount of cells in order to have smaller cells and account for the wall effect here, for the gradients of velocity close to the wall. We have a laminar flow, which is Reynolds numbers of 0.23, so it's very, very laminar, which is good, because we don't have to deal with turbulence, which is also always very difficult. So we filled up in the computational model the L-shaped device completely, 1.75 liters of UHPC mixture with fibers. Everything else is air. And then we apply a fiber volume fraction of 0.7%. And this is not the best simulation, but basically we can follow the flow and see how the flow is affected by the fibers, depending on their location, depending on their concentration, and understand how do they change, how does the flow change because of the applications of fibers. And the best thing is that we can actually follow each fiber over the time. This is a simulation for real time of 9 seconds. This is the 9 seconds that took us on the laboratory to do. And what we have to do now is, in order to have better results on the simulation, is refine the mesh, do a sensitivity analysis on the time steps for the fibers, which is different from the time step from the fluid, and we'll be able to know the location of the fiber, the orientation of the fiber, and the dispersion at every time step. And with that, I want to say that we should be able to study different casting methods, different geometries, different rheologies, different concentrations, different geometries for fibers, different aspect ratios for fibers, and different structural elements. How do we pretend to validate? So we take the actual beam, we do CT analysis, we have histograms and statistics of the orientation and dispersion, and we compare it to the results that we should have when we have our working model soon this year. So I made it quick. As I was asked, this is all the people that are working with us. So far away, the real south, down in Chile. People from MSU, people from FSU, and all the PhD students that are not using kettles from now. So we don't have fires in our laboratory. And I don't know if we have time for questions.